Hello everybody. We are in the last video we were done with the derivation of the equation of the pressure drop, um, and as we said, this is one way of deriving the equations or finding the equations that describe any phenomena is to do this based on theory. And this is what we did last time, and you already saw that the equation was derived for a very special case for laminar flow in circular pipes, horizontal pipes, for Newtonian fluids. So it's not something that we can use as a general equation for different cases. So the what we're going to do today is we are going to go for the second approach, which is using an equation that is produced based on experimental data. And this is the equation that we're going to be using or that's most used in all, I would say most of the applications of internal flow are using this equation for calculating the head losses. So this equation is called Darcy's equation, and this equation is valid for all cases. As I said, it's going to be valid for laminar, turbulent flows, for circular, non-circular pipes, for smooth or rough surfaces, horizontal or inclined pipes. It's valid for any case. Most of the cases, I would say most of the cases. And this equation is as you see here. It's delta P equals F L over D times rho U square over 2. And you would see here all the parameters are known except for this F. We know the length, the diameter, the density, the average velocity, but this F is the parameter that we don't know. So this F is called the Darcy friction factor. It's a factor that's got experimentally, and it represents the friction between the fluid layers and between the fluid and the pipes, the wall of the pipes. And it's if we want to get it or find a formula for this friction factor, theoretically this is how it will look like. But still we will have here the wall or shear stress at the wall, which is, as we said before, it's a parameter that we cannot measure. That's why for the practical applications we calculate this friction factor using or we can use equations that were produced from experimental data to calculate this friction factor. So before we go through the equations that we use to calculate this friction factor, there is something that I want to highlight about this equation. And this is something that I like to do, is to connect what we covered before with what we are discussing now. This is regarding the results of the dimensional analysis. So if you remember in chapter 7, when we did the dimensional analysis, we reached the formula that delta PD over rho U square is function of Reynolds number and the relative roughness. And we said that this delta PL is the pressure per unit length. So we can put it as delta P over L equals rho U square over D times this function. And this is the equation. If I just want to get delta P, it's going to be L over D times rho U square times this function. So this is what we got from the dimensional analysis before even doing anything. This is just what we did. And now when we look at Darcy's equation, this is what we find. So you see that there are common things that we have. We have L over D here, we have L over D, rho U square, we have rho U square here. So we expect by combining these two equations that this F is this. It's a function of Reynolds number and epsilon over D. So this is simple comparison between the results of the dimension analysis and the Darcy's equation. And this is actually what will happen, that we will see that this friction factor is function of both. So we are going to start with the laminar flow and see how to calculate this friction factor for laminar flow. And then we will move to the turbulent flow in the next coming videos. So for laminar flow, the equation is very simple, and this is something we need to be aware of, that the equations are a representation of the systems. So complex systems will be represented by complex equations. Simple systems will be represented by simple equations. And this is a simple case for the laminar flow. So the equation that we use is that the friction factor is a constant over Reynolds number. That's it. So this is the equation that we use. The experimental data showed that there is no dependence on the surface roughness or the relative roughness for laminar flow, only. But in case of turbulent flow, it will be a part of the equation. Okay, so for laminar flow, it's only a function of Reynolds number, and this constant that we have here, it depends on the cross section, the shape of the pipe and the cross section of the pipe. Okay, so if we have fully developed laminar flow in circular pipe, the constant is 64. And an interesting thing that we'll see here, that if we substitute this in Darcy's equation, which is FL over D rho U square over 2, and then put this F as 64 over Reynolds is rho U D over mu, then this is what you'll see. This is Poiseuille equation. Okay, so this is the same thing that we got from the theoretical derivation. So we are getting the exact same output, regardless the way we are doing this. So we can consider Poiseuille equation as a special case of Darcy's equation, as we see from here. Okay, so now let's see what we can do if we have non-circular pipes. So for non-circular pipes, we have already tables for the constants. So if it's a rectangular cross-sectional area, then we need to know the area and the length and the width, and from the ratio of the length to the width we can get the constant. So if it's a square, then A over B equals 1, then we use this constant, and whatever the value, we can get the the value of the friction factor. The same for elliptical cross-section areas. We have the major and minor radii. So if it's a circle, then the two radii are equal, so it's A over B equals 1, so it's going to be 64 over Reynolds, and the same for the rest, just to know the ratios, and from the ratios we can get the constant. And for the triangle cross-section area, if it's an isosceles triangle, then it depends on this angle. So if it's 10, we know the value to 30, 60, 90, and so on. So it's just a table that you get data from. So it's as simple as this. So in general, calculating the friction losses for laminar flow is easy and straightforward, and it doesn't require complex calculations or any long processes. For so this is all, but there is one last point that I want to discuss here, and this is a very important point. This is a very, very, very conceptual point, and I hope you get it. You get it well, understand what I'm going to discuss here. We said before that in the beginning that we are interested in calculating the head losses, and the head losses have units of length. However, here we are calculating the pressure drop. So there should be some way that we can relate this head losses to the pressure drop. So the head losses can be calculated as delta P over rho G. Okay, and the HL is now in the units of meter, and then it's FL over D times U square over 2G. So this is the equation that we use to calculate the losses, and this is what we're going to put in Bernoulli equation. But we need to be very, very careful about something here, and this is the conceptual point that I want to stress on. And this point is, which delta P do we mean here? So I'm going to compare two cases just to make things clear and understandable for you. So let's consider a case where we have a pipe with a large cross-section area, and then this is going through this region where the cross-section area is reducing, and at the other side it's coming at point 2. Okay, the fluid is leaving at point 2. And let's say that this is a frictionless flow, so there is no viscous losses, and we see it's the same height. There is no pump, there is no turbine, so there are no pressure losses. But because of this large area, or the area at 1 is larger than area at 2, the velocity at point 1 is smaller than the velocity at point 2. So the kinetic energy here is higher. And from Bernoulli equation, the energy can be transferred from a form to another. So this velocity increase here means that the kinetic energy increased, and this increase in the energy is coming from somewhere else. So it's coming from the flow work. So the pressure will decrease and the velocity will increase. This is simple substitution in Bernoulli equation. Okay. So P1 is larger than P2, and there is a pressure difference, which is P1 minus P2. But this pressure difference is a reversible pressure difference. It's not an energy that's lost. It's an energy or some energy that are transformed from a form to another. It's just transforming the flow work into kinetic energy. So this energy is not energy lost. It's just transformed from a form to another, which means that if I have another or if this pipe is connected to another pipe with the same D1, the diameter at D1, we will go back to the original state. So the velocity will decrease and the pressure will increase. Okay, so this is what what causes the energy change. It's just energy is transforming from a shape to another. So this is not loss in energy losses. This is energy transformation from a form to another. Okay, so this is not what we meant by this. Okay, this is not what I mean by this delta P. Okay, so this delta P here is just change in pressure because of energy transforming from a form to another. This is not energy losses. What we mean by the energy losses is that a case like this. We have a pipe with the same diameter, with the same the same fluid, same compressible fluid, so it's the same velocity, it's the same height, so nothing changes. There is no pump, there is no turbine, and due to only the friction between the fluid and the walls of the pipe, and between the fluid molecules and itself, there is energy that is lost. So this energy here so this energy losses causes the pressure to decrease. Okay, so this is an energy that we lost, so we cannot recover this energy again unless we put a pump or something, or a compressor to provide energy. But I mean, if we have just this pipe, the fluid flowing without energy transformation from a form to another, the pressure will decrease because of the friction, because of the energy losses. So this delta P, P1 minus P2, is this delta P that we put here. Okay, so it's important to understand the difference. Okay, so the pressure losses, which we calculate from Darcy equation, are what we can use to calculate the head losses. This pressure difference is already in Bernoulli equation. We have P1 minus P2 in Bernoulli, or P1 over rho G and P2 over rho G. So this is what we put in Bernoulli equation. But this losses is what we use to calculate the losses according to this equation. Okay, so I hope this point is clear, and that you don't get confused between these two. Why I have different delta P in the losses than the delta P that I have in the flow, because you will have cases where there is a change in diameter, you have change in elevation, and you have also losses. So in this case, you'll have pressure difference because of the energy change, and also losses due to the friction. So you need to have it clear in mind that they are not the same. That the losses due to the friction are irreversible losses, while the changes due to the energy transformation are reversible changes, and you need to know how to calculate each one of them properly. So I'll stop here. Until next time, we will solve some problems, or I think one or two problems on the laminar flow, and I'll see you then. Goodbye.